Hey everyone, so today is our lesson on matter and change. So our first unit was on lab safety and that equipment, so that's a really quick unit that we went through. So now we are on unit 2, which is matter and change. We got a lot of definitions. Make sure that you are following along with your notes, writing these down so that you could reference them later when we have questions over things, okay? So, first things first, let's go ahead and let's define chemistry, okay? Chemistry, right, is the class you're taking, so let's define this, okay? It's pretty much the interactions of all the material in the universe, okay? So it's the study of the materials of the universe and the changes they go through. Okay, it's water, liquid water turned into solid, okay, turned into ice. It's how your battery works in your car, okay, it's why your countertops are solid instead of liquid. It's why the air that you breathe is in gas form, okay? It's infinite amount of things we could talk about with chemistry. It's one of the foundations of science, right up there with physics and biology. Next thing I want to talk about is the scientific method. The scientific method is the process at which we come up with new discoveries. Okay, it's the process all scientists go through in order to prove things. Some scientists don't go through it, and then we have some instances where we have people that don't believe in vaccines. But if we follow the scientific method, we can make some awesome non-biased discoveries. Okay, so scientific method again is how we discover new things. What we do first, we ask a question. Okay, we ask a question: will this chemical cure cancer? Will this new solar panel give out more electrical output with the sun rays coming in? Okay, we start by asking a question. Okay, 2, we make an educated guess as to what will happen during our experiment. Okay, what is this educated guess called? Hypothesis. Okay, hypothesis. Next, what we do is we conduct an experiment. We have to develop an experiment that works, right? If we are trying to figure out if a certain chemical is good for curing cancer, we're not going to go ahead and test chemicals in water or in a animal like a pig. We might start off with that, but we got to make sure that it works in humans first, okay? So we got to develop this nice experiment to figure out a way that we can get good results that will relate to the real world. 4, we have to analyze these results. Okay? We have to look at the results and we have to look at them unbiased. As much as we might want a chemical to cure cancer, if the results aren't showing us that, then we can't force it, okay? We have to make sure that our results are unbiased and we're analyzing them fairly and not just because we want to find a cure for cancer, okay? And 5 is make a conclusion. Okay, we look at our results, we look at it all together, and we make a conclusion relating back to our hypothesis. Did we prove or disprove it? Okay, so again, non-biased. And then another important thing about this whole scientific method, okay, after we come up with a conclusion, is that other scientists have to show similar results. Okay, so in order to prove your hypothesis, people are going to want to test this. People want to make sure that you're totally unbiased. Scientists have to test this in their lab. That's kind of a big problem with science today, is that all these people are proving things, but scientists want to do their own thing. They don't want to spend time trying to prove other people's research, but it's extremely important that scientists do that. It's good for them to test people's results and make sure that they're getting it right. So that's a big thing that we need in science, is people testing out other people's hypotheses to make sure that they are correct. Okay, so that's extremely important. So that is the scientific method. Okay, ask a question, we make an educated guess or an hypothesis, we conduct that experiment, analyze our results, make a conclusion, and then hopefully other people can test our results, right? That's why we have the big anti-vaccine kind of culture in America, is because those results weren't tested by anybody else. They just made a claim. Nobody verified it or anything like that. And now we have a lot of misinformation going on in our community. So make sure if you become scientists, you are doing your best to follow that scientific method. Okay? Big thing coming up here, matter. Okay, matter. That's what everything is made up of, right? So it's anything that takes up space and volume. So right off the bat, you're thinking of stuff that takes up space and volume. You're thinking of this eraser, marker, the table you're sitting at, your computer, okay? But what about the air? That takes up space and volume, okay? You could feel it, right? It's taking up space, very little space, but it's definitely there, okay? So everything is made up of matter. You're made up of matter. The air around you is made up of matter. The only time where we might not be able to see matter is in space, right? There's no air up there. There's no nothing, no atmosphere. It's just nothingness, absolutely nothing, no matter whatsoever, which kind of is mind-boggling a little bit when you think about it, because how could there be nothing? And it's one of the greatest kind of unknown questions that people are still trying to figure out. What is that stuff up there in space if it's nothing? So that's a fun thing that people are trying to figure out. You might be asking, anything that takes up space, and volume. Those are the same thing. Takes up space and has mass. Guys, has mass, okay? Sorry about that. So, anything that takes up space and has mass. Well, what is mass? You might be asking, if you ever heard anything like that, it's just the total number of atoms something has. Okay, and we usually measure that in like grams or milligrams, and when you're talking about a single atom, you're getting into the 1 times 10 to the negative 32, okay, grams. It's really, really small. So mass is just how many atoms are in this. There's trillions upon trillions, quadrillions, just tons of atoms in this, okay? So that's its mass, how many atoms it's made of. Of course, we simplify it to grams, so this might just weigh 2 grams, so that we don't have to say, quintillions, quadrillions, septillions numbers of atoms, okay? What is an atom? Right? Atoms are the basic building blocks of everything, okay? If you look at the periodic table, those are just atoms, okay? They're just different types of atoms. You got hydrogen atoms, you got oxygen atoms, you got gold atoms, okay? Those are the basic building blocks of everything. And the most basic version of an atom that you might have seen is, I like to reference Jimmy Neutron, right? Is that guy right there. We got the center nucleus with protons and neutrons, and then the outside, these little circles are kind of the paths of electrons. So those are atoms, okay? Those are atoms. And you heard me say the periodic table of elements, okay? And these elements are composed of one type of atom, right? If you have gold jewelry, okay, that's just gold. It's just certain gold atoms, okay? If you have an iron nail, that's just made of iron, one type of atom. Things like this marker are made up of tons of different atoms, made of carbon and hydrogen atoms, probably some oxygen atoms in there as well. Okay, so probably a little bit of everything in this, but an element is just one atom, like an iron nail or a gold ring or pure oxygen. Okay, here I have iron. Its chemical symbol is Fe for ferrous or ferric. Okay, it's Latin. You'll have hydrogen, which doesn't like to be by itself. So even though the symbol for hydrogen is H, usually when we see it in real life, it's H2. Likes to be paired with a buddy. And then you got copper, which is Cu. That's also Latin, like cupric or cuprum, I believe. Okay, so copper is Cu, iron is ferric, Fe. Okay, next up. So element is just one type of element, okay, like iron, carbon, hydrogen, what have you. But what if we mix those elements up? What are those going to be? Well, those are going to be things we like to call compounds, okay? Compounds is a bond between two or more different elements. Okay, we got to make sure they're different. Compound is two different elements. These are things like H2O, CO2. Okay, you got alloys such as brass and steel. Okay, these are compounds. Okay, we got things like H2O, like I said. We got CO2. What else do I have listed? And we got C6H12O6. Okay, which you might know as sugar. Okay, and all of these numbers that just tells you how many there are. This says, hey, I have 2 hydrogens and 1 oxygen. So it's going to look something like that, which we'll get more into later on. Okay, so this is a water molecule. It's got 2 hydrogens, 1 oxygen, as stated here. This is carbon dioxide, so it's got 1 carbon, 2 oxygens. And don't worry about these double bonds. Okay, we'll explain how to figure this out later in time. And then sugar, I'm not even going to try to draw this molecular structure for that, but it's got 6 carbons, 12 hydrogens, and 6 oxygens. Okay, let's get down to states of matter. States of matter. So states of matter is just what kind of form they're in. Gas, liquid, solid, and there's a 4th one, which I'll talk about. Solid, we got a definition for it. It has a definite shape and definite volume. Right? This marker, it's got a definite shape. I can't change it at all. It's got a definite volume. It's going to take up this amount of space. I can't change the volume it takes up at all. Okay, so that is definite shape and definite volume. Next up is liquid. Liquid is definite volume. Definite volume, but no definite shape. Okay, liquid, I could have 50 milliliters of it in a cup. If I take 50 milliliters of it and put it into a vase, okay, it's still 50 milliliters, right? The volume is the same. If I have 1 liter of it and I just put it in a different container, I still have 1 liter of it, but the thing that changes is the shape. the shape is never defined. It fits to its container, right? If I put it in a fishbowl, it takes the shape of the fishbowl. If I put it in a soda bottle, it'll take the shape of the soda bottle. So definite volume, no definite shape. Gas, it has neither. It's no definite shape or volume, okay? It's always moving. It's going inside the room, out of the room. It's moving really quickly. We don't know the definite volume at all times or the definite shape. And the last one, which some of you might have heard of, plasma, which is just high energy particles. You might hear my dog slurping on some water right now. Okay, but plasma, high energy particles, things like lightning. If you go online, you'll probably see something where somebody says there's actually like 16 states of matter. Okay, that's just talking about different mixtures of like solid and liquids, which are actually kind of like colloids or just transition phases where they're in between solid and liquid or liquid and gas and stuff like that. So when you see that, okay, that's kind of getting deep into the rabbit hole. All right, here we're just talking about the main four. And last thing before I end my video, let's look at these guys at a particulate level. Let's look at them if we could zoom in, and I'm telling you, if we could zoom in on molecules, you'd be mind blown by how small everything really is in this universe, okay? And how it's crazy that something so small is what makes up our entire lives. But let's imagine that we got a super small microscope and we could zoom in on something, okay? So let's look at solids. If I could zoom in on an ice cube, okay, and I see tiny little molecules and atoms in there, they would be really closely packed together. Let's say that this is gold, because water is going to look something like, that's a water molecule, okay? But let's look at gold. Gold's just a nice little solid molecule, and it would be just really close and packed together. Those guys are really close, makes it really solid. That's why when you hit it, it doesn't move very much, because you're just hitting a bunch of tightly packed atoms, okay? Liquid, a little bit more spread out, a little bit faster moving. These little lines here shows that they're moving around a little bit quicker. They're not as attracted to one another. They might be heated up a little bit more, okay, a little bit under less pressure. They're able to move around. So when you're able to dip your hand in a jar of water into like a cup of water, I don't know why you'd be dipping your hand in a cup of water, but if you were, those molecules are moving around, so you're able to fit your hand in there, okay? So that's liquid. They're able to move a little bit quicker, a little bit farther apart, but still attracted to one another, still kind of staying together. And last but not least, you have gas. It's moving real quick, okay? Gas molecules are bouncing around. They're all over the place right now as I'm talking. Gas molecules are shooting out and filling up this room as quickly as possible with all their energy, okay? So gas, you can kind of feel when you put your arms around and they're moving really fast. They don't really have containment. They're not too attracted to each other, okay? So that is our first basic video on matter, all right? Another one coming your way real soon. Have an awesome day.